Hello, everyone. Welcome. So here we are going to work on some review problems from the chapter Limit and Continuity. So let's get started with the first example. Example, the graph below is the function f of x. So here is the graph of the function f of x. We have to find these. So in all of these, we are looking at x equal to 2, which is here. So this is x equal to 2 on the graph. Now the first one is we have to find the limit as x approaches to 2 from the left. X approaches to 2 from the left. So when x approaches to 2 from the left, like this, as I'm showing here in the picture, when x approaches to 2 from the left, you can see that this function, the values of the functions are increasing and getting closer and closer to this y value of 3. So this one is equal to 3. Similarly, in part B, we have to find the limit as x approaches to 2 from the right. So let me show you on the graph. So when x approaches to 2 from the right, like that, okay, x approaches to 2 from the right, you can see that the values of the functions are increasing from the right and approaching closer and closer to a y value of 3. So this is also equal to 3. Now in part C, we have to find the limit as x approaches to 2 of the function. So here we saw that from the left and also from the right, that is the left-hand limit and right-hand limit of the function at 2 are equal. So when the left-hand limit and right-hand limit are equal, the limit exists and the value of the limit is equal to these values here. So the limit of this function when x approaches to 2 is also 3. And the value of the function, if you want to look at the value of the function d at 2, the value of the function at 2, it is not defined here. Instead, it's defined here by this black dot there, which is 1. So this is equal to 1. So this is how we can find the limit when the graph of the function is given. So that is first example. Now let's move on to example 2. Here is example 2. So in example 2, we are asked to evaluate the limit numerically. So when you're asked to evaluate the limit numerically, that is, we have to make the table and find the limit. And here we are talking about the limit when x approaches to 0. So if I draw a number line, here is 0. And when I say x approaches to 0, I'm talking about x approaching to 0 from the left and also from the right. X approaching to 0 from both sides. So what we can do here is we can start plugging in numbers somewhere from here, like negative 0.20, and then move closer and closer to 0. And we can do the same from the right. You can start here at 0.20 and then move closer and closer to 0. So we are going to make the table and look at the values of this function when x approaches to 0 from both sides. So let's first look at the left-hand limit. So we look at different x values, negative 0.20. Now we have to go closer and closer to 0. So next can be negative 0.15, then negative 0.10, then it can be negative 0.05, and probably the last one, negative 0.01. So at these different x values, we have to find the value of the function. Our function is sine 3x over x. So we need to find the value of that function when x approaches to 0 from the left. So now, because we are dealing with the trig function, if we are evaluating this at all these values using calculator, our calculator must be in radian. So first, we are going to plug in negative 0.20 for x. And if we do that, we'll get 2.82321. So 2.82321. Now, if you plug in negative 0.15, let's see what we get. I got 2.8 9, 9, 7, 7. So you can see the values are increasing. 2.8, then 2.89. So it's increasing. Now let's go here and plug in negative 0.01. So if we plug in negative 0.01, you will see the value will be 2.95520. Again, increasing 2.8, 2.89, 2.95. Now let's plug in the next one. If we plug in negative 0.05, the value will be 2.98876. Still increasing. Here it was 2.955 and here it becomes 98. From 95, it jumped to 98. So the values are increasing, but they are increasing very slowly. Okay, here it is 2.8, 2.89, 2.95. That's how they are increasing. Now, if we try this one now, let's see what we get. If we plug in negative 0.01, the value will be 0.9995, 2.99955. So again, the values are increasing. And you can clearly see here we started with 2.8. Here it becomes 899. Then it becomes 955, 988, 2.99955. So clearly there is a pattern. You can see that the values are getting closer and closer to 3. That means when we go from the left, the limit will be approximately 3. So we can write limit as x approaches to 0 from the left of that function sine 3x over x is equal to 3. That is the left-hand limit. Now we are going to find the right-hand limit using the similar procedure here. Now I've created the table to find the limit when x approaches to 0 from the right. So I'm starting at 0.20, then getting closer to 0, 0.15 here, 0.10, 0.05, and 0.10. So like in the previous table, what you have to do is we have to plug in different values of x and then find the value of the function at these different values. So now when we plug in these values, this is what I got. You can see these are the similar values as we get in the previous table. So 2.82, then 2.899, 2.955, 2.988, and 2.99. So clearly you can see that the right-hand limit is also 3. So we can write limit as x approaches to 0 from the right of the function sine 3x over x, that is also equal to 3. So clearly you can see that the left-hand limit and right-hand limit are equal. That means this limit exists and is equal to 3. So we can write, hence the limit as x approaches to 0 of sine 3x over x is equal to 3. So this is how we can find or evaluate the limit using numerical methods. So key term here is the numerical method. So whenever you are asked to compute the limit numerically, you must make the table and find the limits. Okay, now let's move on to example 3. So in example 3, we have 2 problems and we have to find the limit, evaluate the limit. Here we are not talking about graphical or numerical. So definitely this should be the algebraic method. Okay, let me draw a line in the middle to separate the work for 2 of these. Like that, okay. Now let's look at the first one. Part A, we have to evaluate the limit as a approaches to 5 of a cubed minus 125 divided by, this is a minus 5. So if we try direct substitution here in the denominator, when a goes to 5, it will be 5 minus 5, which will be 0. So here you are dividing by 0. So that is not possible. We cannot divide by 0. So what you have to do is we need to use the factoring technique. This 125 is a 5 cubed. So you can clearly see that your numerator is like a cubed minus b cubed. Your a is a and b, this 125 is a 5 cubed, so b is 5. And you know the factoring formula, a cubed minus b cubed from college algebra, that is a minus b times a squared plus ab plus b squared. So this is equal to limit as a approaches to 5. If we use the formula in the numerator, that will be a minus b or a minus 5, a squared, then plus ab. A is a and b is 5, so that will be 5a plus b squared. 5 squared is 25 over a minus 5. Now you can clearly see you can cancel this a minus 5 from the numerator and also from the denominator. So you'll get limit as a approaches to 5 of a squared plus 5a plus 25. So now we have the limit of the polynomial function. So if you want to find the limit of the polynomial function, you can perform direct substitution. So the first one is, if you plug in 5, that is 5 squared. If you plug in 5, that will be 5 times 5. And the last one is 25. 5 squared is 25. 5 times 5 is 25. And also 25. 3 25s, that is 75. So the limit for part A is 75. Here we use the factoring technique to evaluate the limit. Now let's look at B. In B, we have the limit as x approaches to 0 of the square root of 4x plus 49 minus 7 over x. If you try direct substitution here, denominator will be 0 again. We cannot have 0 in the denominator. So to find the limit of the function like this one, where you see radical, we have to multiply by the conjugate. So that is, we multiply by square root of 4x plus 49 plus 7 divided by square root of 4x plus 49 plus 7. We multiply by the conjugate or we rationalize it. So here is a minus. When we multiply by plus there, that is the conjugate. And here, the quantity in the numerator and denominator is same. That means we are technically multiplying by 1. So we are not changing the value of the limit. Instead, we are just looking for an easy way to simplify this one. So this is equal to limit as x approaches to 0. Now in the numerator, you have these two quantities exactly the same, and the last two quantities exactly the same, one with the minus, other with the plus. So this is like a minus b times a plus b, which will be a squared minus b squared. So when we say a squared is the square of the first one. When we square this first one, the square root will go away. So it will be 4x plus 49. And then minus b squared, in place of b, we have a 7. 7 squared is a 49. So when you multiply numerator with numerator, that's what we get. Now, when you multiply denominator with denominator, we have x multiplied to square root of 4x plus 49, then plus 7. Now here in the numerator, 49 and 49 cancel. And then we have 4x divided by x. 4x divided by x will be 4. So we can write that as the limit as x approaches to 0. So again, x and x cancel. So we get 4 over the square root of 4x plus 49 plus 7. So now what we see is this x that was making 0 in the denominator get canceled here, and we don't have that x anymore. So now we can perform direct substitution. 4 in the numerator. And if you look at the denominator, if you plug in 0, 4 times 0 is 0. 0 plus 49 is 49. And the square root of 49 is 7. So that is a 7 plus there is another 7. So this is 4 over 14 or 2 over 7. 4 over 14 or 2 over 7. So 2 over 7 is the limit. So what we have done here is in the first part here, we calculated the limit using factoring. And in the second part, we calculate the limit using the rationalization technique. So that's your example 3. Now we'll move on to example 4. Here is my example 4. So example, let f of x equal to mx minus 8 if x is less than -4 and x squared plus 4x minus 4 if x is greater than -4. If f of x is a function which is continuous everywhere, find the value or values of m. So you can see this function, mx minus 8 is a linear function. It is continuous everywhere. Similarly, this is a quadratic function. It is also continuous everywhere. So the only problem we may have is at -4, because this function you can clearly see at -4, this is what is going on here. For the values less than -4, the function is mx minus 8. This side, the function is mx minus 8. And on the other side, when it is 4 or more, the value of the function is defined as x squared plus 4x minus 4. So now for the function to be continuous, the values of these two functions should be same at -4. So we can say f of x, okay, we can say f of x is continuous, everywhere if, now if we plug in -4 here, this one will be, okay, -4 to the first one, it will be m times -4, m times -4 minus 8. And if we plug in -4 here, this one will be -4 squared plus 4 times -4 minus 4. Left hand side will be -4m minus 8. And the right hand side will be, this is 16 and this is -16. So they get cancelled. It is just equal to this -4. Now, if we add 8 on both sides, we get -4m is equal to 4. And if you divide on both sides by -4, you will get m equal to -1. Meaning of that is the function, okay, this function will be continuous everywhere if the value of m is -1. So if we have -1 here, that is -x minus 8, it will be continuous everywhere. And at x equal to -4, the values of these two functions will be equal, and that value is -4. So if you plug in -4 here, you will get a -4. And also here, if you plug in, it will also be -4. So that's how we can find the value of the unknown from a piecewise function to make it continuous everywhere. That is your example 4. Let's move on to example 5. Let's see what we have. Example, evaluate the limit as x averages to infinity of this function. Then state an equation of the horizontal asymptote to the graph of the function, the same function which is here. Okay, so let's get started first with the limit. Here we want the limit as x approaches to infinity of 7x cubed minus 9x squared minus 10x over 11 minus 7x minus 11x cubed. Now, because we are calculating the limit at infinity of a rational function, we divide both numerator and denominator by the highest power of unknown in the denominator. So that is x cubed. So we divide throughout by x cubed. So this will be equal to limit as x approaches to infinity, 7x cubed divided by x cubed, that will be 7, minus 9x squared divided by x cubed will be 9 over x, and then minus 10x divided by x cubed will be 10 over x squared, divided by, in the denominator, 11 divided by x cubed, 11 over x cubed, then minus 7x over x cubed is 7 over x squared. And then finally here, minus 11x cubed divided by x cubed is 11. Now you can clearly see when x approaches to infinity, this quantity will be 0. This quantity will be 0. This one will be 0. And this one will be 0. So what we get is, this is equal to 7 minus 0 minus 0 divided by 0 minus 0 minus 11. Or finally, we get the limit as negative 7 over 11. So the limit of that function is negative 7 over 11. So we can say for the second part, the equation of the horizontal asymptote. So what we get is, when x approaches to infinity, we saw that the value of the function approaches to negative 7 over 11. Okay, that is the key there. When x approaches to infinity, when x goes to infinity, we saw that the value of the function is negative 7 over 11. So this will tell us that the equation of horizontal asymptote, so this implies equation of horizontal asymptote is y equal to negative 7 over 11. So there should be a confirming statement like this to tell you that the equation is like this. So we must write y equal to negative 7 over 11 because we are talking about the equation of the horizontal asymptote. So for the horizontal asymptote, we'll have y equal to. You can also simplify this equation a little bit. If we multiply on both sides by 11, it will be 11y equal to negative 7. And if we bring that on left-hand side, plus 7 equal to 0. So you can write the equation just like this, y equal to negative 7 over 11, or you can write it as 11y plus 7 equal to 0. So this is the best way for us to find the equation of the horizontal asymptote. Always remember, to find the equation of the horizontal asymptote, there must be a confirming statement like this one. When x averages to infinity, the function should go to a finite value. Then only we can say that the value which is here, when you equate to y, that will be the equation of horizontal asymptote. Let's look at next example where we'll also find the equation of horizontal asymptote one more time. Example 6 here. Find equation of all horizontal asymptote to the graph of the function, which is given here. So now, when you're looking for the equation of the horizontal asymptote, as we have seen in the previous question, we have to find the value of the function or the limit when x approaches to infinity. In this one, it was just infinity, but this is more of an open question. So we have to find the limit when x approaches to positive and negative infinity. So let's do two cases here. The first case is when x approaches to infinity. This is also the rational function. There is a x cubed here, and we can think of that x cubed as the square root of x to the 6. The square root of x to the 6 when x approaches to infinity is x cubed. That means to find the limit here, we divide each of these by x cubed. okay? And whatever is there inside the square root, we divide by x to the 6, because when it is x cubed outside, inside the square root, it is x to the 6. So meaning of that is we are getting this limit as x approaches to infinity. When you divide this by x cubed, that is 8, minus, when you divide this by x cubed, it is 5 over x cubed. And in the denominator, inside the square root, we divide by x to the 6. So when you divide this by x to the 6, 9x squared divided by x to the 6 is 9 over x to the 4. 9 over x to the 4 plus 3 over x to the 6. And then plus, this one is outside the square root. So when you divide by x cubed, outside the square root by x cubed, that will be 4. So now, while calculating the limit here, this will be equal to limit. In fact, you don't need to write the limit, because what we see here is when x approaches to infinity, this will be 0, this will be 0, this will be 0. So what is remaining is 8 minus 0 divided by inside the square root 0 plus 0 and then plus 4. So ultimately we are getting 8 divided by 4, which is equal to 2, which is equal to 2. Okay, so that is the limit when x approaches to infinity. So we look at the first case when x approaches to infinity. Now let's look at the second case when x approaches to negative infinity. So let's write that down. When x approaches to negative infinity, you can see the square root of x to the 6 is negative x cubed. That means now to find the limit of this function at negative infinity, we divide throughout by negative x cubed. It is outside the square root. And if it is inside the square root, we divide by x to the 6. So that is the meaning of that. That's our second case here. So we get limit as x approaches to infinity. When you divide this by negative x cubed, that will be negative 8. If we divide this by negative x cubed, that will be plus 5 over x cubed. And in the denominator, when you divide by x to the 6 inside the square root, it will be 9 over x to the 4 plus 3 over x to the 6. Just like our first case here. And then here, when you divide by negative x cubed, that will be negative 4. And clearly, when x approaches to negative infinity, this is negative infinity. When x approaches to negative infinity, this quantity is 0, this one is 0, this one is 0. So what we are getting is negative 8 plus 0 divided by square root of 0 plus 0 minus 4. So technically what we are getting is negative 8 divided by negative 4, which is a positive 2. So in both cases, what you see is as x approaches to plus or minus infinity, we saw that the function approaches to 2. Okay, when x approaches to positive or negative infinity, function approaches to 2. So this is the confirming statement that tells us that y equal to 2 is the equation of horizontal asymptote. So we can write, hence y equal to negative 2 is the equation of horizontal asymptote. So always remember, whenever you want to find the equation of the horizontal asymptote, we must get a confirming statement by calculating the limit. And the confirming statement should be when x approaches to plus or minus infinity, the value of the function should go to a finite value. X approaching to infinity, but the function approaching to the finite value. Then y equal to that particular finite value. Here y equal to 2, okay? Y equal to 2 in this case is the equation of horizontal asymptote. Okay, so we learned how to find the equation of horizontal asymptote. So that is our sixth example. Now we are going to move on to our last example for this video. That is example 7. And here we have the example. Let's read through first. Can the intermediate value theorem be used for f of x equal to 1 over x on this interval to find a real zero? Also, how about 1 comma 2? Okay, so we have pretty much two cases here. So the case one, the first case one is f of x equal to 1 over x on the interval from -2 up to 1. So in this one, if you want to find the value of the function, say for example, f of -2, if you plug in -2 to this function, it will be -1 over 2. And if you plug in 1, f of 1 is equal to 1. So the value of the function at -2 is a negative and at 1 is a positive. So to go from negative to positive, it will definitely take 0. So meaning of that is this implies f of -2 is less than 0, which will be less than f of 1. So if that is the case, if 0 is in between the two functions value, there must be some function's value in this interval, okay, that will give you 0 as the function value. So we can say, so there is c in the interval from -2 up to 1 such that f of c is equal to 0. Meaning of that is there is a real 0 in this interval. So hence we can say there is a 0 of the function. There is a 0 of the function. 0 of the function f of x equal to 1 over x on the interval from -2 up to 1. So that is what is confirmed by the intermediate value theorem. So this statement here, c is in the interval -2 to 1 such that f of c equal to 0. That particular statement there is our intermediate value theorem. So this is confirmed by the intermediate value theorem. Okay, so that is the first part. For this function, there is a real 0 on this interval, and we confirm that using the intermediate value theorem. And we are able to confirm that because the value of the function at -2 is a negative and at 1 is a positive. So 0 is included, or 0 lies between these two function values. So it is just because of that we confirm that there is a real 0 on this interval. Now let's look at the second case. Case 2 now. Case 2, f of x equal to 1 over x on the interval from 1 to 2. So let's see whether we can find a 0 on that interval for the function, or whether we can use the intermediate value theorem to confirm a 0. So here, if we want to find the value of the function at 1, it will be 1. And if you want to find the value of the function at 2, it will be 1 over 2. Now you can clearly see 0 is not between these two values. One value is 1 here and the other one is 2. So 0 does not lie in this interval of the function values. I can write from half up to 1. Okay, between -1 over 2 and 1, we have a 0 there. So the theorem works. But here, between this 1 over 2 and 1, we don't have the 0. That means the intermediate value theorem cannot be used. So meaning of that is, if we write like this, so this implies if I want to write something like this, f of 2 is less than 0, is less than 1, this is not true. This is not true. If 0 is in between the two function values, okay, in between two function values, then we can find, or then we can say that we have the 0 in that particular interval. But that is not true in this case. Okay, this is not true. So we can say intermediate value theorem cannot be used. Cannot be used. So we can use the intermediate value theorem only when 0 is between the two function values calculated on that particular interval at those two endpoints. So in the second case, we cannot use the intermediate value theorem. In first case, we can use the intermediate value theorem and we confirm that there is a 0 on the given interval. So that's how we can use intermediate value theorem to analyze whether we have a real 0 of the function on the given interval. So that is all for this video. That is the last one. Thank you so much for watching. I hope you find this helpful.